Hi, Physics 1, Mr. Janowski here. This is the last video from the whole year. So, just a quick little review of everything we did this year, just to kind of put everything in context. So, let's get started. So, our do now questions. What is the most important thing you learned in physics? Hopefully, you'll remember this forever and for always. It is F equals ma. So here's the basic, pretty elegant version. Here's the vector version, which is the one we actually use. And this is Newton's second law. So, yeah, Isaac Newton was kind of the main character in physics this year. And the other question, what did the Dalai Lama say to the hot dog vendor? He said, make me one with everything. So, for maximum comedic effect, it really needs to be make me one with everything. Because physics, hopefully you saw this year, it is a very unifying science. It is the one set of rules that governs everything in the universe. And if you understand those rules, you'll start to see the connections between everything and how everything is just always following those same set of rules. So here's the map of physics. I will put a description of this I'll put a link to this in the description. And I would actually recommend stopping my video now, watching this video, and then going back and finishing this. This is, hopefully you remember the giant poster we have in the classroom. It's this one. And I love this as just kind of a visual graphic organizer of all the different categories of physics. So, yeah, maybe pause my video, watch this video, and then come back and pick it up. So, yeah, do that now. Now, having watched that other video, let's quickly review the things we talked about this year. We learned the laws of motion. So, yeah, Newton's three laws. Classical mechanics. So, we really started the year with kinematics. So, kinematics is how you learn about, especially the difference between velocity and acceleration. So, yeah, you need a good grasp on those ideas to really get going with this stuff. And then we learned forces and, Newton's laws. Then we did momentum, so our perfectly inelastic collisions and our explosions and the law of conservation of momentum. Then we learned energy and the conservation of energy and the different types of, we had kinetic energy and gravitational potential and elastic potential energy. Then we learned rotational motion and all the cousins and things like that. And then we learned universal gravitation. So that was physics 1. And we did this year, despite the worldwide pandemic, we did basically get as far as I wanted to. We covered all the material. The time we lost and the fact that we couldn't do anything in person, we did lose out on a pretty fun lab that we do in quarter 4. So, that's unfortunate. But yeah, we covered all the stuff. So I'm happy about that. So some of you are graduating and going on to college, and maybe you'll take the physics there. And some of you are not graduating yet. So hopefully I'll be seeing you in physics 2. So here's kind of what we're going to cover in physics 2. We will start the year doing relativity. So the special theory of relativity and the general theory of relativity. So the general theory of relativity is really Einstein's greatest idea. It is huge. It is all mind-blowing stuff. It's really, really crazy stuff. And then we'll go on to electromagnetism. And we'll spend most of the year doing electromagnetism. So relativity, if it's covered at all, if you take physics 1 in college, relativity would kind of more belong in physics 1, but we run out of time, so it doesn't fit in there. So it's a little weird. We start with relativity, then we go to electromagnetism. Now, my plan was, after electromagnetism, to go on to waves, so to study light and sound. Light being electromagnetic waves, essentially. So I would have liked to have gotten that far, but I maybe went a little too slow. And again, global pandemic kind of cost us some time. So we didn't actually get to waves, optics, or quantum physics, which is, unfortunate. So next year, if I see you in physics 2, I'm going to try to tighten up, the stuff we cover, get through it maybe a little bit faster, and then have more time for those things. because optics you can't really understand until you learn waves, and quantum mechanics isn't going to make any sense at all until you learn waves. So let's see. Looking back at here, most of the stuff we do, well, all the stuff we did in Physics 1 is in classical physics, and most of what we'll spend the year on in Physics 2 is also in classical physics. So there's kind of a divide in physics. So classical physics is everything from Newton, or possibly you could start with Galileo, Galileo and Newton, up to about 1900. So about 2+ centuries of physics. And there's a lot you can do with that stuff. So it's science until about 1900, which sounds kind of old and outdated, but it's really what we use all the time. Excuse me. And then at around 1900, there were two big revolutions in physics. The relativity started in about 1905. That was Einstein's miracle year, is what it's called. And if you take Physics 2, we'll cover that in great detail. And the quantum mechanics, that started end of the 1800s, and about the first 3 decades of the 1900s was kind of its golden age, and then it continues on with that stuff. So there is kind of a break in physics. Classical physics up to about 1900, modern physics, everything since then. And there's different ways to divide this. Some people actually classify relativity as going at the end of classical physics, and things are only considered modern if they deal with the Heisenberg uncertainty principle, which is a key idea in quantum physics. But anyhow, if you watch the other video, you will notice this feature right here, this gigantic chasm of ignorance. So real quickly, what is this about? Well, we have basically two modern theories, big overarching theories in modern physics. One of them is relativity. And relativity is basically Einstein's updating / replacement for Newton's ideas of universal gravitation, which explains why Newton's laws of gravitation work so very, very well, and yet they're not quite exactly perfect. So that's relativity. So basically it explains gravity, and it deals with the biggest things in the universe. So that's relativity. Quantum mechanics, and also called quantum physics, deals with the very, very small things. And the basic situation is both of those theories are incredibly accurate in their separate, areas of expertise and their separate realms. So we've tested relativity a bunch of different ways, and it passes all of its tests very, very well. And we've tested quantum mechanics in a bunch of ways, and it also works very well. And quantum mechanics, if it didn't work well, I wouldn't be using my computer right now and talking to you, because all of our modern technology, all of our tiny electronics, it's all based on an understanding of quantum mechanics. Semiconductors, our understanding of those and all the things that those are in, it's really based on quantum mechanics. So we have two extremely successful theories that work very well in their own separate realms. The problem is when you try to bring them together, they don't agree. So we've got a problem. We have two extremely successful theories, and yet we know that both of them are incomplete. They don't quite work well together. So this doesn't have much effect on everyday, walking down the street kinds of things, but it does come into play when you're starting to deal with that first instant right after the Big Bang. And it also, you have to use both of these theories at once when you're dealing with things like black holes. So really extreme situations. And when you try to bring these two very successful theories together, they don't work. They just don't meld. So that gives rise to the chasm of ignorance. So basically, there are a ton of Nobel Prizes buried in this chasm of ignorance right here. So guaranteed Nobel Prizes if you can, dedicate your life to physics and start to close this chasm a little bit and get a way for relativity to play nicely with quantum mechanics. And if you can do that, that would be huge. It would be nice to have just one big overarching theory of that. So that's the chasm of ignorance, which is just a wonderfully titled thing. It's the gap between our two very successful theories. So other places, you may remember we had a graph that dealt with how dark energy and dark matter um, versus just ordinary matter, and how little of the universe we actually understand very well. Ordinary matter, all the stuff on the periodic table, is less than 5% of the total amount of mass energy in the universe, and we feel like we have a pretty good grasp on that stuff. But there's about another 20 or 25% that's dark energy. I'm sorry, that's dark matter, that we can see its effects. We know what it's doing to galaxies, and we can measure it, but we really have no idea what exactly it is or how exactly it works. And then the biggest part of the unknown is dark energy. So this is something like 70 or 75% of all the mass energy in the universe is what's causing the universe to expand at an accelerating rate. And we have no idea what it is. We only found out dark matter we've known since about the 1920s or 30s. We've known it was a thing. We haven't figured out what it is. And dark energy is this we only found out in the late 1990s. So only about 2 decades of even knowing this stuff existed, and we still have no idea what exactly it is. We can measure its effects because the universe is expanding at an accelerating rate, and that takes energy. And we can calculate how much energy there has to be, but we have no idea what it actually is. And is it related to dark matter, or are they completely separate things? Don't fall into the trap that, well, they're both called dark something, so they must be related. They might be related, but we really have no idea what either one of them is. So yeah, we don't exactly understand it. And then in the video, he also mentions, that this cloud of philosophy is kind of hovering over all of physics. And I agree with this. Physics answers the big questions. It deals with the big things. So the whole idea of the nature of reality. Why is the universe the way it is? So you can't start to answer those questions until you have a good grasp of the universe the way it appears to be. So it is a very philosophical kind of science. It deals with the biggest questions. So this is why I love physics so much. And hopefully after taking Physics 1, you're starting to gain an appreciation about that. And hopefully you like physics. So that's it. Happy graduation to those of you that are seniors, and to those of you that are juniors or sophomores. Hopefully I see you next year in Physics 2.